Good evening, guys, and welcome to Tech Tuesday. Today, I'm going to be speaking about the NLP language processing system with spacy using Python and Jupyter. And yeah, so spacy is a library that gives you a lot of cool features to train models to basically what is natural language processing. It is used for sorry, I froze for a second. It is used for sentiment analysis, autocorrection, and cool features like that. That's good, yeah. So, importing spacy, we simply just import spacy itself. From spacy, we have also the matchup classes, which I'll be talking about later, and displacy, which is going to give us some cool visualizations on how the NLP processes work. The first thing we have to do is load the model, and in this case I'm using the largest English model spacy has to offer, but it's usually suffixed with medium, small, etc. And there are many other languages you can use, for example, Spanish. You can train a completely new English model. You can do a lot of cool things with spacing. What is natural language processing? Well, it consists of linguistics, which is the science of language, of how we speak today. And we can add a whole lot of feelings and like emotions, phonetics. We could get a computer to eventually start speaking to us. Well, technically they have. Um, and it's all done through this natural language processing systems. We've loaded the model here. Tokenization is the understanding the words of, any word or symbols available. You also have sentence tokenization, which will break down paragraphs into sentences, and we could relate sentences to one another. But today is just about the basics, so I'm going to just show you a few cool things like word tokenization. And let's just run this. So yeah, we have an index property. It's broken down the sentence into an array and an object that we can access properties from. And the auth is the ID of where the word sits within the vocabulary of the NLP language. This is the raw text, as you can see it, and is alpha would be alphabetical characters, is punctuation would be punctuations, and like a number, is it a number? It picks up alphanumeric numbers. So, for example, the pound symbol would be classified as a number in the alphanumeric sense. Spacy is labels. So Spacy has cool features like giving you labels to parts of speech in the linguistics process, and entity models to recognize certain words and categorize them. And yeah, let's run this. So, for example, ADG, no, ADG, JP, yeah, is an adjective. In subject is a nominal subject, and GPE as an entity is countries, cities, and states. Cool. Let's get down to the basics of linguistic features. Linguistic features, as I said, is the science of language. It's the parts of speech. It's how we say a word. It's the pronunciation of a word, the meaning behind a word, and even down to the meaning of what we felt about what we said. And that's what we get derive sentiment analysis from, is to contextualize that. And with spaces, dependency parser and parts of speech, with understanding the head of the text, we can now make a relationship pattern between the sentence. So, for example, I have here, I had a great time at the beach. We want to give him two more options, say, at the beach, I had a great time, or I had at the beach a great time. So we change the sentences, but using their sentence. If I run this here, you'll see parts of speech, I as a pronoun, in subject, we said was nominal subject, etc., etc. And if you don't understand the spacy labels, because I'm pretty new to spacing, there are a few that I didn't even study in school. And yeah, it's quite amazing because you get a cool effect like this. Where had is the nominal subject to I, and had is the prep word to at. What does prep mean? So I'm explaining what prep is. It's a prepositional modifier, and then an object of preposition. So we start getting like an effect of what the sentence looks like, and we could grammatically then restructure it to create those other two sentences and give options to a user, for example. Predicting named entities. So with spacy, they've already categorized many words. Um, for example, countries, cities, and states will be recognized by spacy. Money will be recognized by spacy. But the cool thing, yeah, spacy doesn't just say, yes, pre-trained entities and that's all there is. It also gives you the opportunity to create your own entities and train models to understand it. And I'm going to show you just now how matches can help with this. Let's run this. Using Spacy's render, we can now have a visual effect of how the word works. So Apple would be an organization, which is true, but in this context it is an organization. But there's an apple which we eat, which you could train an entity to recognize that as food. So for example, Spacey explain again, I don't know what org is, but we do know what country is. And obviously a date, we know what they are. Let's just show it again. So yeah, Apple is a company, or it could be an agency or an institution, and GPE is countries, cities, or states. What is lemma? The lemma attribute. Well, lemma falls under the linguistical properties of spacy, and basically what lemmatization is, it finds the root word of any word. So the inflectional forms, what does that mean? So the prefixes, the suffixes, the past, the future, all of those can affect words and their shapes and add letters. For example, one here gets an extra N, and what lemma does is bring it down to the root word, so it will be easier to recognize later what that word was. But stemming, I don't think spacy has a stemming attribute. There are many other NLP packages out there that offer stemming, but I like spacy in the sense that they went straight for lemmatization, because as you can see, it removes inflectional forms of the word, but one is not a real word because it just removed the prefix. Let's show how lemma works. Basically, we tokenize the word again to get part of the derived properties of the word, and we use the spacy lemma attribute to derive it from the text. As you can see here, am is be, are is be, is being, and that would be the root word, whether it's past tense, future tense, or present tense, for example. Well, present would be, I guess. What spacy matches? This is the fun stuff. Yeah, the real fun stuff. So, matches use the spacy's linguistic features and lexical properties. What does this mean? So, a matcher, let's take a short break from the code and show you a cool site, Software Explosion. So Software Explosion gives you certain things. Well, this section is basically on spacy, and it helps you analyze text without creating too much code to do simple analyzation. So like that display graph. But the one we want to use here is another rule-based matcher. So in a real life sense, we would want to confirm our token, and there's now an automation on most more modern phones. Not my phone, unfortunately. But if you scroll when you get a message and it has OTP in it, and you're on the app that needs the OTP, it automatically fills it in for you. And this is how it would be done. You would create a pattern using spaces. So let's create one quickly and show you the difference between like a number, etc. So let's add a token and show like a number first. And we refresh. And you'll see 2 here gets highlighted, which is not kind of what we're looking for. So let's minus that. Let's actually grab OTP. So we add token, we then go lowercase, because you never know, OTP could be in a lowercase form. You can add another token, and we say it must be punctuation. And yes, true, but we can add an attribute to this, and we can say that it could be optional because there might actually not be a punctuation. We can also add another token, and we want now I'd like a number. And tick it. And let's refresh the text, and you see we get the same result. If I had to remove, for example, this doikies, we can refresh the text, and it still grabs OTP. So the optional parameter allows you to exclude values, and then you can copy and paste this. Nice, copy and paste and add it to your code, and now you have a matcher or pattern to match OTP pins. So let's get back to the code. Yeah, I created 3 patterns. A sports pattern because I'm very into sports. I like rugby, cricket. Emotion patterns. I derived it off a verb, but we could do it over an adjective as well. But basically, yeah, we're using another secondary option towards the pattern where we're using parts of speech with lemma, which lemma will bring it down to the root word. And then a gadgets pattern just to find out all about the latest technology, for example. Then setting a few variables to the patterns. I just added FIFA because it's actually not really Soccer World Cup, it's FIFA World Cup, and rugby because I want to match any document that contains that. Yeah, we can have a list of emotional patterns like love and hate, and different gadgets like a phone and a computer. Yeah, we could even make it a different name or matching name just so that it's more recognizable in the future. But I just went for the basic phone and computer. Adding matches and using a dynamic function to show the matcher. We first take a matcher, we then add the matcher, we add a unique string to the matcher's parameters, and then we pass in the patterns that we want. Yeah, it can be a list of thousands of patterns, depending on what you're looking for, etc. Emotions, love and hate, and then gadgets. We then show the matcher. Yeah, we just want to show the match ID, the string ID, which would be the ID we've given it. Then the starting index and ending index within the tokenized array, and the actual text. Since this is run, we should be able to play this. Oh, that would not be there. Cool. If we play here, oh, let's sorry about that. There we go. Now we got a clearer image. So as you can see here, each match ID is given by the matcher itself, and it's a way to recognize what we are matching. And we have a gadget, and the starting position is at 1 and ending position is at 2, and it's the map. And if you look here, starting position is at 1 and it ends here at 2. So it pulls out map. We've got World Cups, we've got emotion, and if you can start seeing, we are starting to create our own labels and eventually train entity models to understand what we are looking for. Let's just clear this. So what's an efficiency phrase matcher? Efficiency phrase matcher is also, it's pretty much a shortcut. I prefer the top matcher because it gives you a little bit more flexibility. But the reason for that is I have lion yeah in lowercase and lion yeah, but if I capitalize this line and we only want like a little line, which is a cat, we refresh, we don't get that matched line. But with the matcher above, I could use the lower statement or lemma statement to find all lines, or add lemma as a second option. But ultimately I would have to create 2 of these now because we want to identify all of them. Why don't you work now? Yeah, because there's 2 pattern 3s now. I'm say pattern 5 now. We add that pattern to cat. Then we can play it. And there we get cat, as you can see. So phrase matches to me is a bit of a shortcut way of doing it. We just import the NLP vocabulary and then we create matches as we go along with tokenization. So these words would still technically have its own attributes, etc. However, as I said, the matcher above is clearly my favorite. And then basics to similarities and vectors. This is now where we get a bit complex, but out of scope. But I thought it would be fun to show in a percentage way of how I like fast food and I like pizza. It's pretty similar and can be whatever you use it for. Yeah. So basically, we're going to match 2 documents. So a full sentence. We can get similarity between similarities within a sentence. And it's this token versus this token, which would be my index 2 and index 4 of my tokenized array. And I love pizza and soap. What's funny is there's actually a similarity between the 2, but that's because it uses a multi-dimensional representation of the word. So, like the comparison between that. So it can even go down to the letter, and you can see there's O here, O, A, and A. So there is a little bit of similarity. There's even a P for pizza and soap, but we know that they have no relation to each other. Maybe they have a relationship in the sense you use soap to wash your hands after you eat pizza. And then a span and document. This is going to break. Cool. Yeah. A span in this context is a phrase. So from 2 to 5, we're grabbing pizza and pasta, and we're getting the similarity between McDonald's sells burgers. And let's see this run. And as you can see, between the two documents at the top, we have an 81% similarity. What vectors are? Vectors, as mentioned above, is to compare the similarity between the two. Yeah, it's using 300 vectors and 300 vectors between document 1 and document 2. And to show something lastly is the spacy streamlet. So kind of like the website that I showed you, we can now set up a local environment. Say you want to work offline and still have the features of the spacy model. We then just load the models that we want. We can add Spanish, French, whatever we want. We add default text, don't really have to. And then the Streamlit visualization, and it is running at the moment. But you simply write Streamlit run the file name, which would be spacy streamlit.py. And yeah, we have the model set up. We have the 3 different types of models. I can now go, well, the small model, just to show the difference in sizes of the models. Second to load is some certain features like vectors and similarity. No vectors available in this model. You can train your own, but they do offer vectors and similarity to start off with. Yeah, it also gives you a list of attributes for tokens. Then, yeah, so you can have a lot of fun playing around. And let's just show one more model here, the large one that I used. Just give it a second to load. Cool. Seems like it's loaded. So with this model here, we have vector information, which gives you a whole lot of different properties as well. We can now, then this is just between these 2 words. We can now play around between similarities through sentences or text. With the medium model, we also have vectors. Here is using 89,000, and here is only using 26,000. So basically, it's different levels of how spacy has trained their models and giving you flexibility to train a model. Say, for example, this NCore web small. If you want a preset model to have a few entities, etc., and train that model to have a few more entities, you can. I think that's all we have to show today. The matcha. So, if you're really interested, you can go into Spacey, play around, look, read some stuff on models. Um, got API. It's all well documented. Gives you a structure of the language. Yeah, I think that's done. Cool. Thank you for joining me today. I'll look now for any questions to answer, but I hope you had some fun. A little bit nervous, but that's part of life. Um, we can maybe add that to the emotion pattern. Let's see. There is a question that's what is the difference between small and large models? I think I explained that, but I can quickly explain that again. Let's go here. So, in the models directory, let's go to models. So, with Spacey, they have different languages, which is what's what we are trying to use at the end of the day to try and identify certain properties, etc. And the ink core small would be a less trained model. Not to say that it's less accurate, but as the model gets bigger with more things in its vocabulary, um, it it then gets package sized. I don't think all the models are package sized. I wonder actually. I mainly use English, but you can ultimately train your own model, and this is how when you load the model, this is what you have. You have few rules, and you can remove rules. You can remove passes. You can remove taggers just to make the tokenization faster. There's a lot of flexibility with Spacy, and you're more than welcome to go and read up on it. But yeah, for example, you can disable the tagger, the attribute ruler, the lementizer. I think that should technically cover that explanation. Cool. Thank you for joining, and hope to see you guys next time for Tech Tuesday.